All right, so we're talking about ASMs, active shape models, and we were about to start discussing how to, so we've already done the modeling, right? How you create the shape model using per-Christus analysis and PCA, right? List of squares. Okay. And now want to know, now that we have a model, how do we do fitting? So basically, this is how things work. You're first given, or you collect a set of images, right, of a specific object. Then you extract the shape of the object in those images, right, using the low-level and mid-level methods that we have described. And then once you have that, you use the modeling method to create the model of the shape of that object that is given in these images. And now, after you have created the model, you want to see whether that object appears in new images you have never seen before, right? So now you're going to use the learned model to try to fit it in a new image and to see where in the image and in which position that shape is in, or that object. Make sense? Okay. So let's see. So we already have the model. We're given a model, right? The learned model. And now we want to find, given a new image, never before seen, what are the parameters of the model, right? I want to identify the parameters of the model, right? That best explain the shape that we observe in that new image. So as I said, you can use any of the low-level, mid-level vision methods that we have described in the class. For example, you could use edge detection, right? So I'll assume that we're using an edge detector, but everything applies to any other of the other methods that we have seen. Okay? So imagine that you have your object. I know maybe the object is something like this. Okay, so say that this is my object here. And I have my model. And the very first thing that I need to do is initialize the model somewhere, right? The model that I have. So the model, remember, has a shape, mean shape, right? And then the PCs that define how I can deform that model to adapt it to every single instance. So I'm going to do is I'm going to place a mean shape here somewhere, right? So usually what you'll do is you'll detect the centroid of the object, say of the contour points, right? Given by the edges of an edge detector, like the Kenny edge detector. Find this point, you find the centroid of your mean shape, and you align them, and then you try to align all the other points with per-Christus analysis, as we have done before, and maybe you end up with something that looks, I know, something like this, right? Maybe, right? Okay. And then for each of these points now, I'm going to look orthogonally to this, right? So in the direction of the norm of that point, I'm going to look in that direction to see how I need to deform that object, right? What is the deformation of that object, dx, for each of these x points to align the shape into the image, okay? So for example, if I look at this point and look here, I can, for example, find a plot that gives me the value of the edge detector, right? So value of the edge detector in this direction, right? About this axis. You see this? So I compute my edge detector, which is nothing else than the convolution with my linear filter, right, along this. And this is where it's going to be maximum, right, because there is an edge. So maybe the function is going to look something like this, right? And then this maximum is what's going to determine the x that I have to move to actually align with the object. Make sense? Okay. So that's what we want to do. Given my model here, I want to find for each of these x1, x2, x so on, I want to find, say, the direction of x0, x1, x2, x3, and x4 that I need to modify the shape. And maybe some of them are going to go in that other direction, right? So obviously, I don't mean to say that they're all looking inward. Some of them obviously will look outwardly, still in that direction of the normal, right? But I need to modify it in one way or the other, one direction or the other. Okay. So with that, we're going to construct a vector dx that has the x0, the x1, all the way to dxn minus 1 if I have n points, right? Defining the vector that I need to add to x, the position of all my landmark points, in order to move the landmarks to a position that actually match the model. Now, of course, the key to doing this modification is that I have to be consistent with the deformations that the model allows me to do, right? I cannot do any deformation I want. The deformations have to be along the basis vectors, the PCs, right? Sometimes called the modes, that I have extracted. So for this, we're going to use the modeling or the matching that we have defined before. And then remember that we had m, it's our function, the transformation function, which is going to be s, whatever scalar I have now, plus 1 plus ds, right? So I'm going to add some additional scaling parameter here. And theta, actually theta plus differential of theta, or d theta. And this is going to be for x plus dx, right? And maybe we can add here a dxc, which is the additional translation that we want to add. And this has to be equal to x plus dx, right? xc would be the center, right? The translation of the center of my model that I want to modify. Okay, make sense? That's the same equation that we had in our last two lectures. And using the known fact that the inverse function of s theta is equal to m s inverse theta inverse, right? Makes sense that the inverse of the transformation is the inverse of the scalar and the inverse of the rotation. So with that known fact, we can take from here that dx it's equal to m of s1 plus ds inverse negative. Obviously, I should say the inverse of the rotation is probably a little too weird, right? Let me use this other notation, the negative of the angle, right? So if I move 30 in the positive direction, I go 30 in the negative direction and vice versa. Make sense? And so this is going to be now theta plus delta d theta. And then here I have, let's call it y for simplification, minus x, right? I move x to the other side. where y is equal to ms theta x plus dx minus dxc. Okay. Now, in addition to that, we need to make sure that we need to be consistent with the model, which means that x has to be given by the mean x plus pb, where p is a matrix whose columns are the eigenvectors that define the model, right? The eigenvectors that we have defined before. And b, it's the vector of coefficients, right? How much each eigenvector is, or the weight for each of these eigenvectors, how each of the eigenvectors is considered. So we need to find, or we wish to find, the x plus dx that is approximately x bar plus p b plus db, right? So I want to modify the coefficients of my model p such that I approximate this, right? And then, since we know that x is equal to this, we can now say, so thus, say this, thus dx it's approximately given by p db, which is the same as db it's equal to p transpose dx, right? And the last step, I was able to do that because the inverse of p is p transpose, right? Because these are the basis vectors. And that's my result, right? All right, any questions about active shape models? And as always, of course, you have the paper in Canvas, right? Make sure that you look into this. Yes?
For these algorithms, do you always need the same number of landmark points?
Ah, I was hoping someone would ask this. So if you're going to define, so there's more than that, right? So if you're going to define the shape of a specific object, then you intrinsically assume that that object is always given by the same number of landmark points. That's the specific object. That doesn't mean that different objects have to have the exact same number of landmark points, because you can create a different model for each of the different objects, right? But if you want to do then the matching, the fitting that we have done here to find the fitting of the object, then you need to know that that image already includes that specific object, because you need to use that specific model, right? So there are two things that you can do. You can use all the models that you have and see which one gives you the best fitting, right? And that gives you the recognition of that object. So if I try to fit a horse and a car and a table and a banana, and the banana gives me the best fit, then I can assume it's a banana. And every time I do this, I use a different number of landmark points, right? But all bananas are defined with the same number of landmark points. Another solution would be, as we will do later, to use another method to first detect which object you have in the image, and then only do the fitting once you already have a good guess of what the object in the image is, right? Now, there is another problem when you define, which is even more important than this, when you define the landmark points for each specific object. Anyone can think about that? So let's assume that all my instances of the same object, say cars, right? So all the pictures of cars that I have are given by the same number of landmark points, okay? Which, as you can see, it's not ideal, right? Some cars may need more landmark points than others, right? But let's assume that we can solve that problem, which is solvable. It's not very, very easy to solve, but it's solvable. But then you still have another problem, which is, anyone can tell me? And that's what precursor analysis allows you to solve, if they have the same number of landmark points. If not, you can't. No? No one wants to make a guess? Yeah? You want to make a guess?
Well, I mean, isn't it like the permutation of point correspondences?
Right. The point correspondences, right? And that's what the precursor analysis was trying to solve, right? To align the shapes. But if you misalign the shapes, because the points that you have selected are, or the landmark points rather, you have selected are not good enough, then all bets are off, right? So selection of the landmark points is extremely important. Okay.
These algorithms then are also kind of limited to the viewpoint you have of your object.
Ah, very good. Yes.
You can see different landmarks.
Okay. So I'm going to allude to this, but we're not going to cover it in detail today. But there are extensions of ASMs, and the next album we're going to see, which are called AAMs, appearance models, which work for 3D shapes. Okay? And then those 3D shapes, you can align them to any view of the 2D object. But that means that you need, during mid-level vision, you need enough views of all the objects in order to be able to reconstruct the object in 3D, in mid-level vision, right? And that then allows you to create a three-dimensional model. But if you don't have that, then yes, you're right. They have to be the same views. And for many years, in the early competitions of object recognition, all the objects were side views, right? And that's precisely because of that, because a side view of a car versus a frontal view versus a rear view look completely different, right? All right, more questions? Yep. All right. So the next one is active appearance models. And that's just an extension of active shape models. Oh my gosh. So AAMs for short, or AAM, just AAM. All right, so in active appearance models, what we're going to do, we're going to extend the active shape model that we have, but now we're going to jointly model the shape of the object and the shading of the object. And we're actually going to use the shading of the object to guide that fitting that we have here, right? So instead of using edges or any other low-level vision algorithm that we have seen in class, we're actually going to guide the fitting based on the shading, okay? And that means that we need to model both. So we already have the shape model, right? So let's say this is PSBS, right? Which means that the landmark points are given by the mean shape plus some coefficients multiplied by the shape model, right? Now, what we want to do next is to create a shading model. And then for this, what we need to do is, because all the objects are of different size, right? Or not different size, different shape, or slightly different shape, right? All the cars are not exactly alike. So we need to warp them in a way that they are into the mean shape, such that we can actually estimate what is the mean shape, the mean shading model. So let's denote the mean shape normalized image or model as G hat, let's say. And now each image will generate a shading effect by variations of the orientation, the illumination, and so on, the albedo or BRDF of that specific object. So to find a matching, we're going to do a least squares matching as always. And what we want is for each image G, right? For each shape G, we want to do G minus beta 1. Remember two things, right? So this G hat, this is in vector form, right? So this shape or image has been vectorized, right? And now if we want to find the actual shape given the mean normalized shape, we need to subtract this from the vector of all ones. So this is the vector of all ones, right? Actually, let me put it as a row vector. And then scale it by some alpha, right? And now if we solve this with linear least squares, the solution is alpha is G hat times G bar, and beta is G hat times the vector of all ones divided by n, where n is the number of images that I'm using of that object, and G is the mean, right? Okay. Now to find the mean, we already know how to do that. We use the same Procrustes analysis method that we defined earlier. And now with that, once we have all these shapes warped into the mean shape, right? Now we can take the shading of that interior, because they're all the same shape, and we can take that to model the shading of that object, and that model of the shading can be written as G equals G bar plus PG BG, right? Where now PG is a set of orthogonal eigenvectors or modes or basis vectors, whatever, however you want to call them, and BG are the coefficients of these eigenvectors, right? Now, the key, remember that I mentioned of AAMs, is that we're now going to model the shape and the shape in the shading together, because they're both correlated, right? At least there's some correlation between the two. So we can do that. So now model shape and shading together. And that's going to give me B is equal to WSBS and BG, right? Where here W is a diagonal matrix of weights defining the relevance of each of the landmark points, as we had before. Remember that we had this equation of the distance where I had the W diagonal matrix that specified the relevance of each of the landmarks, right? So that's the same one, right? Here. And this I can write it as WS PST X minus X bar, right? This is the result that we had derived before. And now here's PG G minus G bar. All right? And again, this is a diagonal matrix, right? Yes, it's a diagonal matrix of the weights, right? The relevance of each of the landmark points. And now if we want to do the fitting to a new image, once we're done, we want to know how I need to modify an image I. So I need to modify delta I, right? The shading of that image I need to adapt to this. So we want to find really the argument that minimizes the I square. Let's call this coefficient C. So one way to approximate this is with delta C is equal to A delta I, okay? Where C, as above, defines these coefficients that I'm looking for. And now A is just a matrix that provides a linear mapping between delta I, right, the modification of the image that I have to do, and delta C. Now the problem is when you do that, right, so you have an image I, right, or let's call it I, or IT maybe for the test image. And then I set here my I, and I want to add delta I until I fit my shading perfectly, right, to my test image. The problem is that I don't know how to modify the parameters of my model, right? I know I call them C here and B here, but anyways, same thing. How do I modify the parameters of my model given a change in the image? You see that? So I have a shading model, and that shading change, and that shading change has to correspond to some parameters here, right? Yes? And I don't know which relationship there is. I can assume that this relationship is linear, given by this linear function here, this linear mapping here, right? But I don't know that A. So that A, I need to estimate it somehow. And this is the classical trick that people will do. They will get in the training image, right, the sample images that you have, you're going to modify these images with known values, right? You're just going to change the shading of or the value of the pixels in that image, for example, following a Gaussian distribution, okay? So far, so good. And then while you're doing this, you're going to measure, or you're going to compute what is the delta C or delta B that you need to add to your model to get the fitting. And that is going to give you a way to determine A with points here and point here, right? And then you can use linear least squares to find the mapping between the two. So you perturb the image, the sample images that you have, to find that mapping between shading and parameters of the model. All right, so that's a classical extension of AEMs, and that's the most classical way to fit shape models into an image. So you could either use the ASMs, which will require you to use the edges, or some other model that we have discussed in low-level vision, excuse me, or mid-level vision, or you use a shading using this extension of ASMs. Okay? And I've also added this paper of AEMs into Canvas for you. All right. Any questions? So next one is, how do we use the shape analysis methods that we have covered here to do object recognition. And I'm going to say, how about if I say this, object recognition or categorization? Because in your project, you're going to do categorization. You're not going to do object recognition. And there's a huge difference between object categorization and object recognition. Object categorization is when you provide a category of an object. So for example, you say it's a car, or it's a dog, or it's a, I don't know, table, right? Object recognition means that you actually recognize a specific object, right? It could be make and model of a car, or it could be even more specific. It could be my car versus your car, right? Or a specific type of dog, right? A breed of dog versus another breed, or my dog versus your dog, and so on, right? And see where this goes? So when we talk about categorization, we talk about the big categories of objects. When we talk about object recognition, we talk about the specific categories of objects. Okay? All right. So to do object recognition, we're going to use our formulation of shapes that we have given before. Remember that Z, our shape, was given by U minus U bar divided by the norm. So this is the classical mean normalized and norm normalized vector of the shape, where if I have a shape, I don't know, maybe the shape looks something like this, right? Then I have extracted some landmark points from the shape right here, and each of these is, say, x1, y1 transpose, right? And this here can be x2, y2 transpose, and all the way to xn or xp, whatever we have set, yp transpose, right? Yep. And then u, anyone can remind me how we defined u? U was given in the complex domain as x1 plus I y1 and all the way to xp plus I yp transpose, right? And our u bar, it's the mean as always, so p inverse the sum over all i's, xi plus I yi, that's up, right? And let's assume that C is the number of categories, right? Okay. Oh, and let also nj be the number of samples in category J. Okay. So here's an algorithm that we can define to do object categorization or recognition using this shape representation that we have introduced. So first, we define our CJs, which are CJ1 through CJP, actually N, not P, NJ, right? They say, which are all the vector representations of each of the instances of our object for category J. Then we compute the covariance matrix. Okay. Now this covariance matrix, let's call it maybe this sigma j. This is not the sum. This is sigma, capital sigma. Sigma j is 1 over n, zj complex conjugate, right? And of course, j is going to be from 1 to capital C, the number of categories. And because I have the mean and the mean shape and the covariance matrix, that defines a complex normal distribution, right? Correct? Right? So now what I'm going to do, given a set of samples, right, I can construct the capital C models using this approach. Right? So I use this method to create the model, meaning the mean shape, and the covariance matrix that defines each of the categories. Right? And now when I am given a new shape, so given a new shape, we want to find which of these models best describe the new shape. So I'm going to want to find the argument that minimizes, right, the j, that minimizes the distance given by the complex normal, which is given by the covariance matrix. So I'm going to use the inner product, right? Z, complex conjugate Z, it's the inner product that measures the distance, but I'm going to multiply that distance by the metric. And the metric is the covariance matrix, right? That defines the variances and covariances of my model, of my complex normal. And then I need to add, to be perfect, the log of the normalizing constant. So let me call this Cn, complex n of sigma j, where this is the normalizing constant of the complex normal distribution. Now remember, the normalizing constant is the constant that we have in our PDF that guarantees that if I integrate over that PDF function, the volume under that curve is 1, right? That's a requirement for all PDF functions. Any questions? So maybe I'll do that. The constant, the normalizing constant of the normal distribution is the determinant of sigma j over pi to the power of p minus 1, right? This is the normalizing constant that you know from the normal distribution as well. Okay, any questions about this? Nope? Okay. So you can extend this. I mean, this is a trivial, almost trivial algorithm, right? So this is how you construct the model. This is how you do recognition, right, of a new image, right? You find the shape that best models or that best fits the current image, right? Yeah. Now you can extend that by adding the shape model, the active shape model basis vectors that we have defined here, right? So you could also allow this shape to deform, right? In which case then you add the matrix B of the eigenvectors of the shape, deformation that you allow, times the coefficient vector B, right? So you could do that here too, as an extension. Now another way to do that is to change the metric of the space. So obviously the metric that we use here is given by the complex normal distribution, right? This is the metric that I have defined right here, this metric, right? But why do I want to, who's to tell me that the shapes of my object category are distributed in my shape space as a normal distribution? I don't know. Could be distributed according to some other distribution, right? So I don't know. So the way I can test other metrics is by using a kernel. A kernel is nothing else than a metric, or a way to map from one space to another space, intrinsically at least, such that the metric changes, okay? The metric means the way that we measure distances in that space. So specifically, we're talking about, if you have taken my machine learning course, you will know that this is a kernel in a reproducible, what's so-called a reproducible kernel Hilbert space, okay? So we've covered Hilbert spaces in 5460. In machine learning, I cover reproducible kernel Hilbert space, which is an extension of that. And all it means is that you're changing the metric of the Hilbert space, right? With a metric that's defined by an inner product, as always in the Hilbert space. So one way to do that, so say that we wish to define or change the metric. And one way to do this is by defining a kernel function such that if I want to compute the similarity between two shape vectors, say zj and zk, I can do that with any type of function that I want to define. Maybe I'm going to use an exponential function. I don't have to. Just going to use an exponential function as an example. So note that this is just an example here. This is for example, okay? So I could have the negative, and remember that that exponential metric, I have been using this all over this course. We use it specifically in image segmentation, right? As one of the metrics. So I'm going to do zj minus zk, the exponential of negative I theta ik square, okay? And then divided this by 2 sigma square, okay? And what's this? Now this is, I'm going to see if I can scale and rotate that shape zk, right? Remember that this is a rotation, right? In the complex domain that corresponds to the rotation of the shape. So if I rotate the shape and I scale it, can I map it or match it to zj, right? And then I'm going to create an exponential, because the closer I get, the more relevance I have. The farther away I get, the worse it gets, right? Exponentially so. Make sense? All right. This, by the way, it's called, this specific kernel here that I've defined here is called the RBF kernel or function for radial basis function. Okay. Now, the advantage of using this is we can rewrite this kernel as follows by noting that zj minus zk times the exponential of negative I theta jk. Theta jk, remember, it's a rotation from the jth to the kth shape. Thus, let's see, this is equal to zj complex conjugate zj, right? Plus zk complex conjugate zk minus zj complex conjugate zk times the exponential of negative I theta jk minus the exponential of negative, not negative, but I in that case, theta jk. And these two things cancel out. So this is the same as 2 minus 2, the norm of zj complex conjugate zk. All right, great. So it turns out that you can compute that kernel very efficiently, right, by just writing that kernel in this other simplified form. So let me do that. So you can, hence, you can write the kernel from Z that measures the similarity between zj and zk as the exponential of negative 2 minus 2 zj complex conjugate zk over 2 sigma square. Okay. And what is really cool about this is that I can substitute this here for this metric, right? And the reason I can do that is because now, remember, this formulation is invariant to a scale and translation, right? But if I change that metric for that other metric, which is rotation invariant, then I have an algorithm that can recognize shapes that are translation scale and rotation invariant, right? And hence, these kernels are called rotation invariant kernels. Or RIKs for short. So if I need to change my algorithm, so the algorithm that I have here, now I'm going to compute kj as phi of zj transpose phi of zj, where phi is the RBF kernel that we have defined here, right? Or whatever other kernel we want to define. Okay. And then what I can do is I can compute the eigenvalue decomposition of this. So kj delta j let me say 1 to specify this is the first eigenvector. Delta J1, lambda J1, right? This one specifies this is the first eigenvector, or the eigenvector associated to the largest eigenvalue. Okay? So this is the largest eigenvalue. And then if you do this, then classification as above, by above I mean I wrote on the other side of the board, then classification or categorization of the shape is given by the argument j that minimizes, I'm sorry, that maximizes rather, should be, because I'm taking the largest, that maximizes the sum of k, z, z, I don't know, let's call them, what am I using? Maybe n, z j1 over lambda j1, right? Square root. And then n from 1 to nj. Okay. Now, as always, remember, I see you take pictures as always, but I also posted that you're welcome to do it. Go ahead, don't be shy. But know that the paper with all these equations is also in Canvas, right? So there's always a paper or book in Canvas that you can follow. Now, all this that we've covered to this point only works for 2D shapes, right? So precursus analysis is great when we have two-dimensional shapes. But what happens, as we said earlier, if we want to do 3D shapes? So I'm not going to cover this in detail, but I'm going to briefly tell you the obvious extension that we can use to obtain or to model 3D shapes, right? Now, if we go back to 5460, you'll remember when we introduced a fine structure for motion that we talk about a famous theorem by a guy named Conjuring, right? The famous affine structure for motion theorem that shows that with two projections, I can define the shape of a three-dimensional object, right? So you can use the exact same trick here to model a kernel, say, a metric that measures the similarity in one of these projections and the similarity on this other projection, as long as these projections are not parallel to one another. So they don't have to be orthogonal, but they cannot be highly correlated, right? They have to be different projections. And then you measure the similarity in both, and then you create a kernel between these two. So let me show you very briefly, just a summary, but the details are in the paper, how we could go about doing that. So if we have an object that looks like this, okay, so we have an object that looks like this, and now what we're going to do, we're going to take two pictures of that object, maybe one picture, we're going to take it from here. So I'm going to do a projection, and I'm going to obtain a picture of this that maybe looks like that, right? So that first image, let's call this Z2, and the other Z1 image, maybe I'll take it from here, right? And that other image, I'm going to call it Z1. And then I can create my Z as a vector with Z1 and Z2, right? The two representations of the three-dimensional shape. And then I'm not going to write down the kernel There are a lot of derivations that I have to go through, but you have those in the paper online in Canvas. You can redo all the kernel steps that we have done for 2D for this new 3D model, and you end up with another kernel that measures the similarity. There's translation, scale, and rotation invariant in 3D space. Okay? All right? Good. Any questions? So I want to talk now very briefly about a couple of applications then of this, so that you get a better idea. And then later tonight, we're going to post a project on categorization of objects from shape, based on shape, right? So base shape categorization of objects later out. And it's up to you to decide which of these methods or any variation of this method that has been published, or you could, if you want, derive your own method, right, based on all these ideas to do categorization of objects. As always in the project, the goal is not to get the best possible results, but to do a good job showing that you understand the basic concepts, right? And that you can justify your choices and you can use a method that is appropriate for that problem. Okay, so maybe I'll start with which one? Well, let's do the gate recognition first, maybe, and then we'll come back to objects again. Or should we do objects first? Let's do objects first because we're already in object recognition. So I'll do matching deformable shapes. So we wish to match shapes in the real world that may differ, maybe different at what we'll say, and we're still talking about 2D shapes, by the way, that may be different at multiple scales, or as the paper that I posted in Canvas say, resolutions. And the idea is very simple. So imagine that you have a curve or a shape that looks something like this, and another that looks maybe something like that, right? So let's call this shape A, this shape B, and we note that depending on the resolution that we look into, these shapes look very similar or very different, right? So maybe this represents a 6 or a G, right? The shape here, and this a U. So they're probably very different shapes to us, right? But at certain regions of the shape, like this one and this one, they look exactly the same, right? And this part here and this part here look exactly the same, and this part here and this part here look exactly the same, right? So we need to distinguish what we mean by same or different depends on the scale that we're looking at. In contrast, if we we're looking at a shape that maybe looks something like this. Okay, this shape right here versus, let's see if I can do that. This shape right here, we'll probably say that shape A and B here are extremely similar to one another, right? They represent the exact same object, but that's at a big scale or resolution, but at a finer scale, they are very different locally, right? So the question is, how are we going to define a method that can deal with these variations, okay? So let's see how. And this is just one possible method, obviously, as always. So what I'm going to do, I'm going to define the shape A as a set of landmark points, let's say A1 through AN. Okay? And that could be, maybe I use parentheses here because the paper uses parentheses. I think it would be more appropriate if we just said a set, okay? Like this. So let A define an open curve. I'm going to assume that it's an open curve, like this one that I've shown here. If it happens to be a closed curve, right, if it's closed, then A1 has to be equal to AN, right? That's the only constraint. So if I have a shape like this, I'm going to have some landmark points here, right? A1, A2, A3, A4, and so on up to AN. Now, let's define, let AI be a midpoint of A, capital A. Okay. Now, if that is a midpoint, I can then divide that shape into two subshapes, right, or two partial shapes. So this yields let's say A1 that goes from A1 to AI, and capital A2, which goes from AI to AN. Right? Yes? Now, one way to represent this is by defining that shape that we have here, right? A1, AN, and maybe AI somewhere in between the two. And now that partition means that we take this, right, and we divide this into two sets. In one set, I have the shape from A1 to AI, and in the other one from AI to AN. Now, for each of these, I could recursively apply the same algorithm, right? And I could have a shape here that goes from AI to AJ, and this one from AJ to AN, and so on, right? Yep. So In that way, I can construct a tree that represents the shape that I have at multiple resolutions. Okay? Now, once, so let me call this partition, by the way, let me call this partition here. Maybe this is a function that does this partition, which I'm going to call Li given capital, L of AI given capital A, right? And now, given a model of that shape A, I want to see whether this is similar to my shape B, right? So some shape B. So let's see how I may be able to do that using the things that we have covered in class. So now given a new shape B, that's going to be given by B1 through Bm. And let's also assume that B1 is equal to A1 and Bm is equal to Bn, sorry, An. Yep. Right? Okay. So we have that. Now, we wish to find, so, okay, let's say that. Let, or given, rather, given that partition that we have done at point AI, right? We wish to find the Bj, right, that creates a tree for B that is equal to that tree that we have constructed over there, right? So that has to be up to translation, scale, and rotation, always, right? So for this, we can define it as a recursive function. So psi or psi, what's this? Psi? Okay. Of AB, this is the minimum of the Bj that minimizes psi of A1 B1 plus A2 B2 plus lambda A of some norm of LAI given A and LBJ given B, right? For some norm L, let's call it capital L. So this is some metric that I'm going to use. So this, what it does, it recursively calls the same function, right, for each of the nodes of that graph, of that tree, right, recursively. And when I get to the very last one, right, I measure the similarity between what is represented in these nodes, and then I go back up, right, adding that similarity. Lambda A, it's a scalar larger than 0. Okay? And this is a metric of the similarity between two shapes. So for example, the precursus distance, right? So we're generally going to just use the precursus distance here, right, as that metric. Now, two obvious extensions of this. I mean, this is a very simple algorithm, works really well, but there are two extensions that can make it work in real images much better. One of them is by adding local deformations of the shape. If we only have one shape A, we cannot do that, but if A is given by a number of samples of that shape, then we can compute the covariance matrix of those, and we can compute the eigenvectors of that covariance matrix, which gives us the possible modifications, right? The transformations that I can allow to this, right? So that metric then can include that deformation as well. And another thing that you can take into account is what happens when there are occlusions, right? So if that similarity is not possible because that portion of that shape is actually occluded by some other object, right? And you can actually get rid of that. See that? Okay. All right. Any questions about this one? Yeah, question.
Object has to be symmetric. What if we have a shape where symmetric?
Oh, no, no, it doesn't have to be symmetric. No. Right. This could be something like this, right? Doesn't matter. And then in that case, this would be here, AI to AN, right? And so on, right? Absolutely not, yeah. And it can also be closed.
How will we scale invariant? What if you have your B is in a different scale?
Oh, that's where you're going to use this function, right? You're looking for the BJ, right? You are basically scaling the, okay, here. So if I have this one here and this one here, right? You're looking for that B1, A1, so you're going to align these two, right? So this is going to be something like this, no? AN and BM, right? And now you're going to look for that point, that midpoint, that matches this, right? Okay. And then in that metric, you can add scales with it's Procrustes distance. So you can add the scale, translation, rotation, right? That's a Procrustes distance. And you can then add deformations of that shape if you have multiple samples for A, right? As a covariance matrix, right? More questions? All right, another paper that I posted in Carmen applies this to gait recognition. And what that means is that, and they are mostly side views of people either walking or running or pushing objects or doing certain activities, and you want to recognize the gait of that individual, right? And categorize it in some of these categories of motion. And let's see how this works. Oh, are we out of time? I think we are out of time, right? Yep. Okay. All right, so I'll do that next time. And then I have just a couple more things to talk about, the shapes, and then we'll move on to other types of object recognition. All right? I'll see you next week.